Hello, ladies and gentlemen, and thank you for stopping by. Welcome to this ASM webinar, an automated micrograph analysis to save time and costs. I'm Fran Richards, Editor-in-Chief with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series, designed to provide information you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. The series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is MIPAR Software. MIPAR Software is an innovative image analysis company and the makers of MIPAR Image Analysis Software. MIPAR is a novel image analysis tool that allows users to reliably extract and measure from their images. Handling challenging applications in everything from material science to photography, MIPAR has facilitated automated solutions to hundreds of practical problems. More information can be found online at MIPAR.us. We're proud to have MIPAR software on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 866-952-8437. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time by using the Q&A window located in the lower right corner of your screen. Click the question mark button to open the Q&A window. Type your question in the box at the bottom and click the send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the material community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies, such as nanotechnology, and management topics of interest to scientists and engineers. AM&P E-News, a bi-weekly publication, delivers updates from the metals and materials industries. Subscribe online today at asminternational.org. With that, I'd like to introduce the presenter of today's webinar, Dr. John Sosa. Dr. Sosa is the CEO and co-founder of MIPAR Software. He received his PhD in Materials Science and Engineering from The Ohio State University while focusing on 2D and 3D microstructural characterization of titanium alloys. It is a pleasure for me to introduce John.
Hello, good morning, good afternoon to wherever you're speaking from, or to wherever you're joining us from. We really appreciate you giving us an hour of your time to hear what we have to say today. Thank you, Francis, for that introduction. As was mentioned, my name is John Sosa. I'm the CEO and co-founder here at MIPAR. Clients have come to us when they need effective automated solutions that work for their problems. Not canned solutions that, of course, demo great, but typically fail in real practice. Not code-heavy solutions that require a CS degree to develop and are usable by one or two people, but effective automated solutions that overcome challenges often that other products could not, that are developed rapidly and are easily implemented at their site for their problems. So today, we are going to speak about three of those. We wish we could cover more. Here at MIPAR, we have constructed over the last year and a half over 700 custom solutions to automate various problems, many in materials, but also many in life science. We thought heavily about what to present today. We wished we could have included applications like phase analysis, pores and cracks in additive materials, carburization, porosity, retained austenite measurements. These are all applications that we've built custom solutions for. And we chose to settle on these three because of the predominance that we've seen our clients request them. We've seen many grain size examples, but a growing number of particle examples. In fact, an overwhelming number of particle analysis applications in the last few months, especially with the explosion of additive manufacturing and the role that particle quantification plays in that space. So, as was mentioned in the chat window, MIPAR was featured on the cover of ASM's flagship magazine back in January. We had a cover article in that issue, and we discuss in detail the grain size application I'm going to present. We mention and discuss in detail general particle analysis applications, not specifically these two, because these recently emerged from our clients as solutions developed in the last month or so. And we decided to include them again because of the overwhelming number of particle problems that we see coming to us. So on the grain size end, to be covering a case where the client decided to graduate from EBSD imaging, but was able to image their microstructure in a way that automated software could handle. They knew the cost of using EBSD solely for grain sizing, for those of you unfamiliar, electron scatter diffraction. But they were, again, able to collect images that software could handle. You'll learn through the use of MIPAR to come up with an automated solution, to increase their grain sizing by 100x, save over $500,000 in cost for one sample lot. In the second case, we'll be covering challenging outer particle detection, overcoming obstacles like handling overlap particles and ambiguous boundaries, and that's required in order to accurately make size measurements from the loose powder via image analysis. And in the third case, we'll focus more specifically on satellite detection, not only detect satellites, but classifying whether they're a satellite or not, and then developing a very custom quantification scheme that allowed the client to measure the percent satellization, if you will, in the particles. So let's move into the first case study. Like I mentioned, this was an industrial client who had been stuck using EBSD alone for grain sizing. Now, EBSD is fantastic for crystallographic texture, for getting the orientation of the individual grain, but they didn't need it for that purpose. They were merely using it in size because it was the only way they could get an accurate segmentation and therefore get an accurate grain size. Manual analysis was completely out because of the overwhelming cost and time intensiveness of it, not to mention the subjectivity, especially with this microstructure where boundaries are fairly ambiguous. And so the primary technical challenges, as you'll see, stopping other products from properly recognizing the grains were the faint, often very subtle contrast at some of the boundaries, and even more importantly, the need for a software algorithm to connect the dots, so to speak, and do what the human brain does so well, which is estimate where many of these boundaries lie, but can be quite challenging for software to do. And then lastly, they didn't just need to measure images, I'm sure many of you are aware. They needed to collect fields in the tens or hundreds, and then aggregate the grain sizes from all of those images into a single histogram to get a single grain size mean, min, and max. So all three, that last one in particular, they had been unable to find to their satisfaction in the solutions available to them. So what we're going to start with now is diving into the software for a live demo of this case. Processor and post-processor used. I'll also mention as well, if you haven't noticed, that the cover article I mentioned is available as a handout for your download right from within this webinar. So to begin, let's open an image. It's trivial. Just drag it in from your file browser and it opens up. We can go in and inspect. We have this side-by-side view that we often overlook as we've used this software so heavily, but our users point out is immensely valuable to always have a before and after of your original image state and your processed state. And you'll see this in action. So you zoom in and you can see subtle, faint contrast at boundaries. You can see incomplete boundaries. Now, my brain is pretty good at estimating where those completions might be. So you'd love for the software to do the same. And how we'll judge the success of this is whether the grain size we measure from this image, or this set of images, matches their ground truth, or what they think the true answer is, from their EBSD measurements. And that comparison is discussed in more detail in the article. So let's load the recipe that was created for this. Our team, working with our client, created this recipe in under a working day with absolutely no programming involved. To load the recipe, either drag it in just as we did the image, or load it from your recents menu if you've loaded it previously. This is sort of your private recipe library. So the recipe loads, and here we see the detection results. Now, if you are familiar with MIPAR, you'll know you can unlock this and go into detail mode, get completely under the hood, and make infinite numbers of customizations to the algorithm, or to the recipe. Today we'll be in simple mode, where all you see are the key settings for the key steps that have been exposed to the user, as well as the layers, and when there are measurements, those as well. The layers are the different classifications of features that have been picked up on by the recipe. Layers can be shown, hidden, renamed, recolored, of course. And what we have here are two layers. The first is all of the grains, and the second are just the complete ones, or the ones that don't touch the edge. And this is what the client wanted their size measurements made on. So the first key setting you'll see here is the crop image. This, I'd just like to quickly mention, can be very useful for focusing in on exactly where in the image you want to analyze. We hear this question a lot from our clients. Can MIPAR let you zero in on a particular area, not the whole image? And the answer is absolutely yes. For example, for now, this crop has been used just to include the data bar, or exclude the data bar, but you could adjust this and change your area of interest, drag it around, and the algorithm then executes on exactly where you told it to. I don't have time to go into it today, but we can also handle non-rectangular AOIs easily as well. So on to the second step. This was key in picking up on the very subtle contrast. So as you zoom in here, you'll note that there are areas that are just barely darker than their surroundings. And this boundary detection step uses a local contrast detection function that doesn't care about how absolutely dark something is, but rather how dark it is relative to what's immediately around it, much like your eye works. You know that I want to select this as some boundary, not because it's the darkest thing in the image, but because it's darker than what's immediately next to it. So that's what the boundary setting does, or the boundary detection. And initially, these are all named, in image analysis terms when you build the recipe. But as you see, they can be renamed to friendly terms, not image analysis jargon, even with custom notes written as to what each setting does. The connect boundaries then is what does the heavy lifting here and allows these educated estimate boundaries to be drawn in, allowing for a proper grain size measurement. So we can go here and take a look at what this particular step is doing. We can toggle it on and off, and you can see how it has attempted to draw separations between the invisible or along the invisible boundaries in order to estimate what the true grain structure is. Again, much like our eye does, but can be challenging for software. And lastly, then we have a minimum grain size setting. Nothing under 4 pixels is allowed to pass. This was just the internal standard that the client was used to using, so we built it in to the recipe. Of course, this can be set in physical units, but we left it in pixels for this solution. Now, rather than make measurements from this one image, as you'll see done later on, I want to demonstrate how the solution allowed the client to batch process many of these images with this recipe, and then make the measurements from the whole set once the batch was complete. Now, before I do that, in order to make measurements of grain size in something other than pixels, you've got to calibrate the image. You've got to set what's known as the scale factor, or how big a pixel is in physical units. We open over 150 file formats. Many of those have metadata built in, and we can pull that out and use it. But in many cases, our users use basic TIFFs or JPEGs or PNGs that don't have any of that scale factor metadata. So in that case, we need to calculate the scale factor from something that has a known distance, say a scale bar, like we see on the original image. And that's done using the calibration tool. We use the opened image. There's a bar down here that we know is 5 microns long, and MIPAR will even find your scale bars for you. It'll put a line across it. You say that's 5 microns, and now you have your scale factor. That scale factor saved into the recipe, and it can now be used for this magnification and imaging resolution. So into the batch processor, we load the same recipe from the recents menu. We go and we grab the set of images to batch process, and we click go. It runs through them, and then the view results button lights up. Click view results, and you can now review the batch. This is something that our clients have pointed out can be immensely valuable. The ability not only to process images in batch, but to actually see what the batch does before you make the all-important measurements. As I'm sure many of you know all too well, your measurements are only as good as your segmentation. That is, your measurements are only as accurate as the accuracy with which those features are found by the software. It doesn't matter how many measurements your software can perform. It doesn't matter how many standards it can spit out. If the features are not found accurately, the measurements are no good. So the ability to perform some quality assurance and supervise your images prior to measuring them is key. Now, once the post-processor is open, it will pop up the process images automatically. I'll just drag in the session file from a previous run so we can take a look. So here we see all of the processed images, all of the grain detections, and we can flip through and see how well the detection worked on each of them. We can make manual corrections in here if we need to with Photoshop type tools, freehanding, drawing in pen lines, clicking and erasing. This is a facilitated batch review and correction environment where you can clean up things that you need to prior to making the all-important measurements. So when you're ready, in this case, we're just going to look at an overall grain size distribution. We're going to do that in the measure features environment, since that is that is the type of measurement this is. This is a measurement on a per feature basis rather than a per image basis, which is what these checkboxes offer. So hit measure features, and this client wanted to use caliper diameter to measure the size of each grain, or the longest line that fits inside of each feature. So we check caliper diameter, view measurements, and we're just going to make them from the complete grains. So what it's doing now is measuring every grain from every image and putting it into one column for you. Click the column that you want to plot, and there is now your overall grain size distribution across as many images as you batch processed. We have a mean size of roughly 700 nanometers, a min and a max standard deviation shown. This table can be saved. These graphics can be saved. The summary stats can be copied. And what gave this particular client immense confidence in this method was that they produced nearly identical grain size distributions from their EBSD grains as to the backscatter image grains. So because of this now, they were able to adopt this MIPAR solution. What used to take them roughly 10 hours per sample, which meant that they could process roughly 240 samples over 4 months. And that was a fairly standard batch for them. They were able to use backscattered imaging in the SEM. That takes roughly 50 seconds per image. They were able to do 240 samples in 1 day instead of 4 months. And that saved their SEM operational cost. That saved them roughly $575,000 in SEM operational cost. So that is this case. Let's move back now to the slides and go through the first particle example. In a hard place, so to speak. Their two options that they had faced months ago were either inaccurate automation, to use software that they knew weren't finding the particles accurately, or hand tracing every single particle in every single image. Even that they didn't have immense confidence in, because two people would trace the particles 2 different ways. But manual tracing was completely off the table because the cost of doing so was through the roof. So they had to resort to software that was not finding the boundaries correctly, but it was all they had, and it still allowed them to get some measurement of shape. So we work with them to understand the challenges here. They were quite unique, I must say, given the range of particle examples we've seen. Clusters like this, they wanted counted as 1. They wanted clusters where there wasn't a clear, dark separation between particles to be classified as 1 feature, but particles like, let's find one over here, particles like this, even ones like this, where there was some visible boundary between them, needed to be separated from one another. And most importantly, this had to work on more than 1 picture. It could not require tweaking settings image to image to produce reasonable results. Otherwise, they might as well start hiring a fleet of interns to trace all their images. So let's move into the software and just take a look at the solution. But you can already see from this view what the MIPAR solution was able to do. You've got particles like this. You've got particles, tiny ones, sitting on top of other ones that the software has isolated. And the client, after reviewing the separation, gave us the thumbs up. They felt that all the requirements had been met. Overlapping ones were captured, fine ones were found, and these challenging, rough ones were also accurately found. That allowed us to make accurate measurements, as I mentioned before. So let's move back into the software and take a look at this in more detail. So again, I will drag in one of these images from our file browser. We'll clear out the recipe. But one like this that needs to be separated. These tiny particles that sit on top of others need to be found separately, and these tiny ones that sit on the floor need to be found separately. Also, if you look down at particles like this, you might not know it just at a glance, but there's a considerable fade off in intensity as you move towards the edge of the particle. And in fact, at the very edges of a lot of these, they're the same color or the same gray value as the background. And this poses a challenge to accurately trace this outline without picking up a bunch of stuff in the background that is not particle. So let's take a look at the recipe and see how those challenges were addressed. So you'll see some measurements pop up here first. We'll review these in a bit. But I first want to focus in on the different layers and then work through the key components of the algorithm. The ones in red are ones that we are confident enough in the completeness of the particle in order to measure their shape. The yellow ones are ones that the software has deemed are too occluded by other particles in order to get an accurate measure of their shape. This was something the client initially had concerns about. They asked how, when you have a particle sitting on top of another one, that was impressive to be separated from its parent in the first place, but how do you now deal with something like this Pac-Man shaped particle being inaccurately measured as rougher than it actually is? And our solution, rather than try to estimate where the particle boundary is, even though that would be not too difficult for that case, but with something like this, we can't reliably estimate where this boundary is when we can't see it. So we decided, let's just flag the ones that are too covered and not measure their shape. We've got plenty of particles to measure. We can batch process hundreds of these things. We're not starving for statistics here. So that's what the colors mean. Now to walk through some of the settings, as I mentioned, we use a marking and then extend the boundaries approach. So this brightness marking step here aims to select areas that we're absolutely confident are parts of particles. And then the rest of the algorithm takes this marking and snaps it to the boundary edges. This is a very powerful approach that lets us do what the human eye does so well, which is take areas that you know belong to your features and then snap those areas out to where the feature ends. Now, the separation was the next hurdle. We had to accurately, again, cut particles like this that had some local darkness between them, but not cut particles like this, where if you're familiar with something like a watershed approach, we'll go crazy and make cuts based on these, you know, this hourglass type shape that's starting to emerge there at that neck. So we used a combination of our local subtle contrast detector and our separate features tool to really give the separate features tool some help and say that you're only going to draw your lines where there's strong enough local darkness between particles. That's what the separation darkness sets, is that critical darkness that an area has to have locally in order to be cut. And then our separate features tool goes in, as you saw before, and completes the cuts where we ask it to. Then some other stuff happens afterwards to refine all of those outlines, and we end up now with our classification of measurable versus not measurable, for shape purposes, that is. So to talk about those measurements, let's move on down to the bottom. We have two measurements set up for size and shape. The shape one let's cover first. And again, the shape measurements are only going to be performed on the red particles, or the orange ones, I suppose. So to make those measurements, just click play. And what we'll now see is not just a table of measurements, which is great, not just a histogram of measurements, which is arguably better, but a color coding, a visualization of where these measurements sit in the image. This can be a very valuable tool, not only for identifying where measurements might reside in the image. You might have local clustering of rougher particles in one area than another, but it really helps you understand the significance of these measurements and understand what they are telling you about your features. There's nice interactivity between the table. Click on a cell, and that feature is highlighted in the image. Click on a feature, that cell is highlighted in the table. So you can get an immediate understanding of what the rougher ones look like versus the smoother ones. In this case, reds and yellows are very rough. Blues are rounder and smoother. You can even indicate where on the histogram these different particles sit. Again, all of this data is exportable into your reports. The stats are copyable. And if we want to switch now to taking a look at eccentricity, we can do that. Just switch the column. Here, darker reds are nice and round, where brighter yellows are more linear or more elongated. And there's many other size or many other shape measurements that MIPAR can produce. Roughness and eccentricity tend to be our two most commonly used. Roughness, I should have mentioned, is a measure of sort of how abstract or how much concavity a feature has. So a starfish would be a very rough shape, and a nice smooth circle would be a low rough shape. Roughness has a minimum of 1 and a maximum of infinity, and it is used quite commonly in the particle analysis space. So let's move on to size now. And with size, I want to mention that the client did not set out expecting to use image analysis for particle sizing. They had a laser-based spectroscopy approach where they would pass a powder sample through a laser, they would get diffraction from the laser, and they would then have a plot of what the expected histogram of particle size was. They weren't able to see the particles, as you know, with that sort of method. They just flow a bunch through the laser setup and they get a plot. And what they came to realize was that their plot was wrong. They were missing a lot of fine particles in that plot because those fine particles were stuck to bigger ones and were getting counted as one. So a fine particle like this, or what you'll see all over the place, tiny ones sitting on top of others get grouped into that cluster and they get missed in your size analysis. So once they saw how accurately these particles, these tiny ones, could be captured, they moved to using image analysis for their sizing, with the added benefit of being able to see what you're measuring. So to take a look at size, we can click on the second row and hit play. Now, I should mention we chose to include all the particles for the size analysis because the sizing is done with the same caliper diameter as you saw with the grains. And even though these yellow ones are fairly covered, they're exposed enough for us to get an accurate measure of that caliper diameter. We don't actually need to see the whole thing to be able to measure its size accurately. So we hit play on this. And now we're looking at a size distribution. Again, you have nice explorative abilities in your quantification. And as with the grains, what this client wanted to do is aggregate size measurements across many fields at once and put it into one population, into one histogram. But in order to do that, this solution has to be repeatable. It's got to work just as well on the next image. So to take a look at that, let's just drag in another image and say reload. The next image comes in, the algorithm re-executes, and you get its result. So a little bit of this gave them great confidence that, yes, the solution is working on all of their images they collected. So they then proceeded to batch process and produce an overall size histogram, just like you saw with the grains. So prior to MIPAR, this client was knowingly using another automated tool that was inaccurately capturing their particles. It was cutting them where they didn't want. It was missing ones that were sitting on top of others, but it's all they had available to them. Manual tracing was completely out of the question, way too costly. With this solution in place, they were able to graduate to an automated solution that they felt was accurate and get the best of both worlds, the speed and the accuracy and the reproducibility. So let's move back now into the slides and take a look at our last case study. Again, we thought we needed to do it justice. We've got many examples of porosity detection. Honestly, the materials applications are about as diverse as you could imagine, and the life science ones too. We don't have time to go into any of the common life science applications that many of you might be familiar with, colony and cell detection and counting, but those are there too. So if you don't see the application that you're working on, we'll talk about that in a little more detail at the end and what we encourage you to do. So on to the final case. Again, this was another particle analysis example, but it was a different one. They were measuring their particles in cross-section. They didn't. This client didn't feel that they could reliably identify what was a satellite from a loose powder sample. There might be particles sitting on top of other ones that aren't truly bonded. They just are statically connected. So in order to get a better satellite analysis, they embedded their particles in a binder. They used an instrument known as a RoboMet 3D, made by a company UES in Dayton, Ohio, to iteratively mechanically polish and optically image their material, thereby collecting a whole set of 2D slices from this embedded powder mixture, such that they could then batch analyze for satellite analysis. However, they had a few commercial tools available. They had the open source ones that I'm sure you're all familiar with. They really didn't have a problem identifying particles. Those are pretty bright relative to their background, so a quick threshold does about what they need to. But that didn't help them. They didn't need to find particles. They needed to find what were satellites, what were parents, and then construct a custom measurement approach without having to spend weeks or months writing code and ending up with a solution that one person in the company knew how to operate. They could not figure out how to use their commercial tools to get this done, and they were fairly stuck because this was a consulting client that had to return this analysis to their customer in fairly short order. So, as was the case with all of these solutions, our team created this recipe inside of MIPAR graphically without any programming inside of a working day, and we're able to put it into deployment the next day. So the challenges here, as I mentioned, were to not only separate these very subtle satellite particles, but identify them as satellites separately from their parents, and then configure the measurement formula that gave a percent satellite measure for the entire mixture. So let's take a look at how that was done. So just like before, we see key recipe settings, the classification layers, the measurements that are run, and measurements pop up immediately on load. We'll revisit those measurements in a second. Let's first take a look at some of the detection or segmentation. The green ones are what we call clean particles. Those are ones that aren't parents of satellites, and they don't have any satellites connected to them. The pink ones are parents of satellites. Those are ones that are parents of that have satellites connected to them, and then the orange are the satellites themselves. Now, a little back note, I guess, on how this classification was done. Again, first the detection was done with somewhat of a basic thresholding. A critical value was chosen to define what is particle and what is not, and that's exposed here as an adjustable setting. A similar minimum size, like the grain size study, was set. In this case, the client didn't want anything under 5 pixels to count as a feature. And then we'll touch on what this manual tool allows. But the separation was done with a combination of our separate features function for obvious ones like this, but then some pretty powerful morphological functions strung together to allow you to cut these very subtle satellite separations and cut them free from the parent. Now, in order to assign a particle as a child or a parent, you really couldn't just use size relative to what was around it, because sometimes you have satellites that are roughly the same size as what they're connected to. What it really is about is sort of how far extended that feature is away from what it's connected to. So, as many of you know, with MIPAR, you have an image processing playground at your fingertips. You can string together functions graphically, visually, interactively in ways that you may have never even thought to with other platforms, and come up with truly unique algorithms and solutions without writing a single line of code. And that power was used to develop this classification algorithm to say that if, let's consider the whole cluster, all connected, look at its centroid. Where is it? Somewhere around here. Now let's cut all of the things free and say that the one in the separated set, the one that touches the centroid of the whole cluster, we're going to call that the parent, and the rest the children or the satellites. And that logic was put together for this purpose. So with that all done, we built up the measurements. And what you see here now is a count of the number of particles that are so-called clean. the number of ones that have satellites, the number of satellites themselves, and then the total number of particles. And the percent satellites here is satellites over total times 100. And that again was built without any coding and conformed to what the client needed to deliver as a measurement to their customer. But this is great to show on one image. However, a repeating theme is they want to produce measurements from more than just this one field of view. They actually want to count up satellites across many images and express the satellite percentage from looking at all of those fields together. So back into the batch processor we went. We ran many fields. They collected over 100, I think, through this recipe. And we ended up then back in the post processor where we're able to take a look at the detection results. So just like before, we can flip through the different images and assess for ourselves how the detection worked. And then to make their overall satellite analysis measurements, we chose count. So you want to make a count on these two layers across all images, and then they get a report per image. Now you could calculate a satellite percentage on a per field basis if that's the way your experiment was set up. In this case, they chose to sum this column, divide the two, multiply by 100, and that was their total satellite percentage. Now, the last thing I'll point out is oftentimes you need to just get in there and make a quick fix on a detection or on a classification. There's sometimes no substitute for the hybrid between human supervision and automation. And we've taken great lengths to facilitate that as much as we can. So as an example, let's say that even though the software didn't think this was a cut, for whatever reason you wanted to call this a small satellite. A manual edit step like this allows you to do just that. You click edit, you just come in here and make a cut, and the classification then updates in real time for you. That can even be done in batch by making that step interruptible. And for each image, the user will be prompted to make any corrections needed before the batch goes on to the next one. And that has allowed some very challenging problems to be addressed, still lead to orders of magnitude speed increase, but still allow the human to assist the automation and reach the accuracy and the validation required. So that's what I had for this final case study. Let's go back now into the slides and review. First case, they were using EBSD imaging just to collect a grain size distribution. It's the only thing that could reliably find the grains. It took them about 10 hours a sample. They were able to use a MIPAR solution, replace their EBSD imaging with backscatter imaging, which took a minute per image, and process a load of 240 samples in a day instead of 4 months. The cost and time breakdown and calculations are described in much more detail in the cover article that is in the handout section and that we've mentioned before. In the second case, the user was stuck using inaccurate automation to produce inaccurate shape measurements because it's the best that they had. With a MIPAR recipe, they were able to reliably separate overlapping particles, even tiny ones that sit entirely on top of bigger ones, and they were able to preserve these more complex clusters and not over-separate them, because once they do, they really couldn't get an accurate shape measurement. And as an unexpected side benefit, the ability to accurately capture these small features that sit on top of others allowed them to switch to image analysis for their sizing and get a much more accurate size distribution than their laser approach allowed, since their laser approach grouped clusters like this into one feature and didn't count the size of the small ones. And then in the last case, MIPAR, in under a working day, was able to provide this client with a automated solution, not just for finding particles, not just for separating the satellites, not just for classifying what's a satellite and what's a parent, but for providing a complete solution to take raw measurements and produce an automated metric of percent satellization that technically didn't exist inside of MIPAR until that very day. That solution was built from the ground up without coding for that particular customer. And that's really our main point. We are a solution-driven company and product that work with users of all types. Whether you are someone who doesn't know the first thing about image analysis, but just needs results. In fact, we find many folks aren't even aware that they do image analysis. We have metallographers tell us that, no, they don't do image analysis. Well, we ask them, well, what do you do during the day? Oh, we sit at the microscope and we look at the microstructure and make assessments. Well, that's image analysis, just not computer aided. So if you are looking to automate quantification in a reliable way, but don't know very much about the computer-aided field of image analysis, our environment allows our team to custom build these solutions for your particular problems and give you an environment to drag and drop them and get the results that you need. Of course, we are here to not only consult during the solution development phase, but train your team as to how to deploy these solutions. And we have a diverse set of self-learning materials, from our user manual to our tutorials online, but also our MIPAR Academy, which is a self-paced Udemy course that teaches you the fundamentals of image analysis and how something like MIPAR can help you apply them to solve real problems. That's available through our site. It's no cost. And lastly, our recipe store, where if you didn't see your particular application showcased today, we encourage you to take a look at the recipe store on our site. It's a library of over 50 pre-built recipes for applications all over the place, not just in materials, but in life science and even other fields. And those are just a taste of example applications that MIPAR can address. You're welcome to download those and the example images and run them. But as you've seen today, we have worked with many clients from academic to industrial of all sizes to develop custom automated solutions for them that meet their needs and fill their gaps and address their real challenges. Now, on the image analysis expert side, it's I think it's unique that the same environment that allows image analysis beginners to run complicated solutions is the same one that allows folks that have been doing this all their life a very powerful playground for them to create algorithms from scratch, very visually, very interactively, perform these what-if scenarios about how to go about solving these puzzles, and come up with solutions either orders of magnitude faster than other tools have allowed, or to reach problems that they simply couldn't before. You've seen you can build in the exact amounts that your users need into the recipes, pop up on load. And I mentioned briefly that we also have an API available that will allow you to run recipes in your applications if that's the type of solution that you need. So we definitely encourage you, if you have automated micrograph analysis that you've either struggled to perform satisfaction in other tools, or if you're looking to try to automate something you haven't been able to automate before, you're stuck doing a lot of manual tracing, or you're concerned about variability from person to person, we encourage you to get in contact either through email, give us a call, submit it on our website, chat with us on our website. Our team is here to build solutions. With that, I thank all of you very much for your attention, and we will now open it up for questions and answers.
Well, thank you, John, for the excellent presentation. We do have a few questions that have come from our participants, so let's get right into those. We'll take a few of them. Can you measure ASTM grain size with this?
Or some of the others, we can report grain size measurements that conform to those standards, or at least as much as the software of the standard asks for, and also, unitless ASTM grain numbers.
Very good. Another question here. Could FEA be useful with a micrograph, considering a grain being a node?
By FEA, I'm assuming we mean finite element analysis.
Mm-hmm.
I'm not clear what the intent is. Is the intent to take a segmented grain structure from an experimental image and then subject that to an FEA simulation? If that's the case, that has been done, in fact, in 2 and 3 dimensions. I've had users use MIPAR to try to estimate the number of grain boundaries that exist in the image, or the number of triple points, and then compare that to what their simulation gets. So feel free to, reach out to us offline if that wasn't the answer that you're looking for, and we'd be happy to talk through it some more.
Okay, great. Well, we have time for one more question. Is there any development to perform analysis to quantify phases, specifically if there is something to quantify the amount of retained austenite in a carburized part?
Sure. We've built many solutions for retained austenite quantification. It really comes to your particular imaging method, your sample prep method, your imaging instrument. What is it about the retained austenite in the image gives it away as retained austenite? If it's its color, or its gray value, or its color, whatever it is, we can develop an algorithm so that the software knows retained austenite and what isn't. And then certainly once that's done, quantifying the percentage in the image globally or locally, or whatever you want to measure it, is very likely once the solution or recipe has been built to detect it. But we've certainly developed retained austenite solutions.
Okay, very good. Well, thank you everyone for those excellent questions. If we didn't get to your questions, please, our presenter will review these questions after the presentation, and in a few days, all participants will receive an email with further contact information. I encourage you to complete the brief survey that will appear on the screen as you exit the webinar. With your input, we can continue to provide webinars with high-quality, practical information that you can use. I also encourage you to follow up with John for more information about using automated micrograph analysis to save time and costs. Once again, I'd like to acknowledge the sponsor of today's webinar, MIPAR Software. Handling challenging applications in everything from material science to aerial photography, MIPAR has facilitated automated solutions to hundreds of practical problems. For more information, visit MIPAR.us. Thanks again for participating in this ASM webinar. Have a great day, everybody.